We were discussing compactness and we proved some properties, equivalent conditions of compactness. Compactness is equivalent to sequential compactness, and it is also equivalent to the set being the metric space being totally bounded and completeness. There is one thing you should know. This is a remark. Compactness is a topological property. Topological property is something which is determined by the collection of open sets. Need not be, maybe there may be two different metrics. Metrics may be two different, but then the open sets may be same for two different metrics. The open balls may be same. So they are equivalent metrics. So, but compactness depends on the open set only. It is defined as compactness is it is defined through open cover having a subcover. So it is a topological property. It depends on only open sets, the collection of open sets. Compactness is a topology. On the other hand, which is equivalent to complete, this depends on the metric. Totally bounded, which also depend on the metric. Okay. Something may be totally bounded in one metric and it may not be totally bounded in the other metric. They may give rise to the same open sets. See an example. But then somehow these two together is a topological property. That's what this says. And for example, if you take n with respect to discrete metric, d1 equal to mod n minus m. This is discrete metric. Each singleton is open ball and all sets are open sets. And n with respect to 1 by n minus 1 by m. We have seen that this also generates the discrete topology. If you have any n, then the nearby n plus 1, n minus 1, if you take something smaller than that, I mean, so radius smaller than that, you will get the singleton. So both generate discrete topology. Discrete topology means all sets are open sets. That's what it means. Both generate discrete topology. But then n with respect to d1 is complete. N with respect to d2 is not complete. Right? We have seen. On the other hand, n with respect to d1 is not totally bounded. N with respect to d2, d1 is complete is clear because any sequence is a Cauchy sequence if and only if it is eventually constant. So that's why that is equivalent to convergence. Here d2, there is a sequence, there is n. This sequence n is Cauchy because it is just 1 by, I mean, the distance between them is 1 by n minus 1 by m, which goes to 0. So this is n, this is a Cauchy sequence, but it doesn't converge. Okay. I mean, it has a limit infinity, but which is not there in the set. Okay. I mean, intuitively, the limit is infinity, which is not there. But n with respect to d, so if you take d1, that metric, it is not totally bounded. This clear, it's not totally bounded. If you take any epsilon ball, that's going to be singleton, and there are infinitely many balls, disjoint balls with radius any epsilon, right? Epsilon is small, the ball is going to be just singleton n, and there are infinitely many disjoint balls that cannot be openly bounded. Any metric space with infinitely many disjoint open balls of radius epsilon cannot be totally bounded. On the other hand, this is with respect to d2 is with d2 is totally bounded. I mean, that's also easy exercise. If you take, if you take 1 by n less than, if you given epsilon, someone said something. If you take any given epsilon, if you take some 1 by n naught less than epsilon, okay, then b of n naught with epsilon will be all those things, right? I mean, it depends on, it contains at least this n naught infinity. I mean, n naught, this set, n naught plus 1 up to infinity, all those things. Okay. Then there are finitely many things that can be covered by epsilon radius. Maybe, I mean, it may be bigger enough. You don't need all of them. They have the same topology. One is complete with respect to totally bounded, complete with respect to that, not complete, not totally bounded, but totally bounded. Yeah, it is with respect to one metric, it is totally bounded. One with the other metric, it is completely complete. But then they are all metric space property. But together they are actually, which is a topological property, it doesn't have it. That's all. I mean, just an example. Okay. Just to remember that they are all topological property. I mean, not topological property, totally bounded is another thing.
For complete also rebounded, we consider another metric space with the same topology, then prove that, and hence we can prove the.
Say it again. If you have one topology,
to prove some property in a completeness of compactness or totally bounded, then you take another metric space with the same topology, then prove it on that. That will imply.
Prove it on what?
Take a new metric space with the same topology.
With the same topology.
On that metric.
Complete and totally bounded. Both. Yeah, yeah.
Whatever you want.
Yeah, whatever. Yeah. No, that's what compactness depends only on. Yeah, exactly. That you can do. Correct. If you want to do only worry about both, I mean, completeness and totally bounded with respect to another metric, it is true with respect to this. That's correct. Yeah. This is another remark only, but it's sometimes used. This is sometimes used. Maybe I need the definition first. You have a collection. We have a metric space. Sorry, Fi. Maybe an uncountable collection. Is a collection of open sets. Is a collection of closed set. Collection of closed set is said to have has finite intersection property. Said to have finite intersection property. Finite intersection. This is just I have to record it. That's all. This is easy property, which we call it as FIP, finite intersection property. If you take Fi1 intersection Fi2 intersection Fin is not equal to empty for all I1 up to In contained I finite. Okay. You take any finite collection of this indexing set. You have a collection of closed set. You have a collection of closed set. If you take any finitely many of them, finite sub collection, then their intersection is non-empty. That is what it means by. That is what it means to have finite intersection property. Okay. Then the proposition whose proof is immediate. If X is compact, okay, then Fi in I has finite intersection property, implies F is compact is equivalent to, I will write it down. This is for all. Equivalent to for all Fi with finite intersection property. If you have any collection of closed set with finite intersection property, then intersection Fi in I is also not equal to empty. Okay. This is easy. You just have to see that Fn, Fi has finite intersection property. This is equivalent to saying Fi complement I in I is not an open cover. Okay. So this is just that. Then it's clear. Okay, I don't have to write the other reasoning. Okay, if it is compact, every open cover should have a finite subcover. So if it is is equivalently saying if some collection of open sets which does not have any finite subcover, okay, if it has finite intersection property means no, wait a minute, sorry. This is not an finite intersection. No, sorry. But this is not correct. Sorry, what I wrote is not correct. Okay. This just has that Fi complement does not have finite subcover. Finite subcover. Okay. Okay. This has finite intersection properties equivalent to saying this finite subcover. And another thing to notice is intersection Fi is not equal to empty. This is equivalent to saying Fi complement is not an open cover. Okay, these two statements. Okay. I'm just saying that Fi has finite intersection property. That is, if you take any finite intersection, then the intersection is non-empty. That means if you take the complement, their union cannot be whole thing. Okay, so Fi has finite intersection property is equivalent to saying Fi complement does not have any, does not have any any finite subcover. Okay. Now, if something is this is not equal to empty, is equivalent to saying Fi is not a open cover. Okay, open cover does not have finite subcover. These two they are equivalent. That's all.
Complement should be X.
No. If it does not have a finite subcover, that cannot be open cover. That is same thing as saying every open cover has a finite subcover. Every open cover has a finite subcover is equivalent to saying if something does not have a finite subcover, it cannot be open cover. Fi complement does not have a finite subcover. Fi has finite intersection property. No, wait. Fi has let me explain. Fi has finite intersection property is equivalent to saying this collection, this open collection, does not have any finite that does not have any finite subcover. Okay, and this intersection is not equal to empty is equivalent to saying this is not an open cover. Both are correct, right? If intersection is not empty, you take the complement. Okay, that cannot be X. So union of the complement cannot be equal to X. So that is not an open cover. So this says that, so this condition says that if you have anything with finite intersection property, then the intersection is not empty. Whole intersection is not empty, which is equivalent to saying by these two conditions, if something does not have any finite subcover, then it's not an open cover. Which is same, if there is an open cover, there will be a finite subcover. It's also same thing. Okay, it is just like usual logic. That's all. Okay, there is nothing to prove. Same statement. Okay, same equivalent statement. Okay. So let's discuss continuity. Okay. So position X is compact. Okay, and F is a function from X to Y because they are all metric spaces. Okay, there is continuous is equivalent to saying F is uniformly continuous. Continuous is always uniformly continuous. Okay. So I think that can be proven in many ways. We will use the okay. We have to take an epsilon greater than 0. Okay, that's okay. We want to prove everything continuous means it's uniformly continuous. There is no function which is continuous but not uniform continuous. That's what this says. Automatically it says it's uniformly continuous. Okay. So we have to use the property of the continuity and prove that it is actually uniform continuous. So given epsilon, we have to get a delta such that the continuity condition is satisfied. That's for all xy. Okay, you have x minus d of xy less than delta will imply f of d f of x f of y is less than epsilon. Okay. 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 To prove that for x in X, let Vx equal to f of b of f of x epsilon. Okay. This set is open thanks to continuity. Thanks to f. Okay. Since f is continuous, this is open. I take the inverse image of the open ball around this f of x epsilon. Okay. This is an open set. Okay. Then union of x in X, Vx equal to x, of course. This is an open set containing X is in Vx. So this is an open cover, of course, right? So it's an open cover. Okay. Okay. Huh? After here. Open thanks to F being continuous. F being is F continuous. Okay. Since F is continuous, that is, we are using the F is continuous. Okay, F is continuous. Or since okay. Now there is a finite subcover. We want to get a delta, right? So this is compact, so it is sequentially compact, which implies there is a Lebesgue number. Okay, so there exists delta greater than 0. Okay, recall what is Lebesgue number. This is the definition. There exists delta greater than 0 for any x in X. There exists for any y in X. Okay. Yeah, I haven't seen anything. I have just taken the open ball and taken the inverse image that just covers it. There is nothing has been done. Okay. So because it's an open cover, which is clear, there exists a delta greater than 0 such that for any y in X, okay, there exists a x something in the open cover, there exists a Vx such that B of y delta is completely contained in Vx. Okay, this is just the definition. We have proved that if you have any open cover, if the space is sequentially compact, which is equivalent to compact, then there is a Lebesgue number delta, and that is this. There is a uniform delta you can choose, so that there is always, because y is in Vx, there is always there will exist some delta, but you can fix a uniform delta for all these things such that this is there. Okay, this is the definition of Lebesgue number, and Lebesgue number exists for this cover. Okay, okay, now we are done. This delta should work. Okay. Now, okay, now if Z is in B of y delta, okay, that just means y and z are in Vx. Okay, but then this is just the inverse image of that. That just means d of f of y minus f of z r. But this is at a distance epsilon from f of x, so this will be 2 epsilon. So I call it as, take it epsilon by 2 if you want. Okay, I mean, you can take it to be, doesn't matter. You can take it epsilon, you will get 2 epsilon. You can take it to be this. Okay, that's what we want. We want it, right? Get them. You can prove it in other ways also. Okay? This is what we wanted to prove. If z is in B of y delta for any y, and I mean, this is just equivalent to, I mean, d of y z is less than delta for any y and z. Okay, then this is true. D of f of y f of z is less than epsilon. So this is what we wanted to prove. This is what uniform continuity means. We have got a uniform delta for any y and z. Okay. Okay. So this is very easy. This is just for record. X is compact. F from x to y continuous. Then f of x is compact. So what is your proof? There are many ways of arguing it. What is the proof? Huh? Yeah, you have an open cover of this. Okay, that will have, you want to you take an open cover of this. You want to get a finite subcover. Just take the inverse image. That will be an open cover of that. That will have a finite subcover. Then push it. If you take the image of that, that will be a subcover of that. Right? F inverse F will give the same thing. Okay, so because of that, or sequentially compact you can take. You can take any sequence here. That will be inverse. There will be a subsequence which is convergent. If you because it's continuous, if you take the image of that, that will be, you get a subsequence. So both ways it's clear. Okay, it's clear. Okay. Yeah.
Open cover. You can have a finite circle.
Yeah.
You take the minimum radius, that will also work as
well. I believe so. If you take the finite subcover, you take the minimum, maybe exactly not this. You have a finite subcover. Huh? You, mm,
like radius of the largest ball inside. Radius could be arbitrarily larger.
yeah. Yeah. No, no, Vx can be RB, as he says, Vx, there is nothing to do with delta. You want to get a delta, not some Vx or something. You will get a Vx. What is the minimum? Minimum of what you are taking?
I'm saying the maximum of an open ball inside. Okay. Minimum
of, you want to take a minimum of radius, right?
Minimum of radius. By radius I meant the radius of the largest open ball inside.
Largest open bar inside.
Radius of a, by a radius of a.
That will be, that will not be a smaller one, no? Smallest one, no?
Radius by an open set. I mean the radius of the largest open hole inside it. Okay. And now you have a lot of open balls. For each Vx you have a radius and minimum of it.
Right. But why should
it's an epsilon. Now, since f is continuous at every x, you have a delta such that the ball of x around delta is contained inside the ball of fx around epsilon, of that ball.
Yeah, yeah.
Then you take the minimum delta. I think that's
no, minimum delta of what? You need finitely many of them. No? You will get I mean, you are using totally boundedness.
Around, you have open ball around every x.
Okay.
There is some non-zero delta around every x.
Okay.
You take a finite subcover.
Yeah, the same thing. Yeah, finite subcover. That is what totally boundedness is for delta. So you take the, that should work better, write it. I mean, once you write it will be clear whether it follows or not. Okay. I'm sure there are many ways because, I mean, those arguments are anyway contained in there exists a delta, right? So it should be there. Yeah, this just looks simple, that's all. Okay. So, we have already proved it. Okay. So, yeah. Okay, that's done. So this is just f is from x compact, f is from x to R. Okay. Then there exists okay, the supremum and infimum are attained. Sure, it is clear, right? Proof is clear. So f is continuous. You have compact, f is continuous, then there exists supremum and infimum are attained. That's what this says. So f is compact. So f of x contained in R is compact. That is equivalent to, that is closed and bounded. Okay. So infimum is a number, real number. Supremum is a real number because it's bounded. Okay. Infimum and supremum. So infimum of f of x is in R. Similarly, supremum of f of x is in R. Okay. I mean, compact implies closed and bounded. Closed is clear. Totally bounded implies bounded. So we haven't directly proved bounded, but totally bounded will imply bounded. Okay. So these things are there. Now, if infimum is something, some number, some m, then there exists some sequence here which converts to this. Okay. Converts to this. So, I mean, then because it's closed, that has to be in there. And that is what it means by there exists in x naught. Should I write all the thing? There exists xn converging to, sorry, f of xn such that f of xn converge to m. But since this is closed, since f of x is closed, there exists a x naught such that f of xn converges to, I mean, m is equal to f of x naught. That's all. I think this is clear, right? This is compact, this is closed and bounded. So infimum and bounded means infimum and supremum are some real numbers. Okay, it's not minus infinity or infinity. So they are some real numbers. So, but then since it is, but then by definition of the infimum, there will exist a sequence in this set which will converge to that. Supremum, same argument. Okay. So f of xn will converge to that. But since it is closed, this f of x is closed, that should be inside f of x. That means there exists a m is equal to f of x naught. Okay. It just, that means that. Okay. So it is clear. If it is not clear, you ask me. Is it okay? Huh? Yeah, that's what I used. I used f of x is compact, right? F of x is compact. It means closed and bounded. Bounded means supremum and infimum exist as real numbers. Then there is a sequence converging to that, and because it's closed, it's there. Okay, all these arguments are there. Anyway, you write down and convince yourself. Okay. There,
That itself implies
If-
contained limit. You don't need to.
use what?
Like, that's fine. That's the argument. But infimum exists as it is closed.
No. Real number itself is closed. Why infimum exists? Yeah. It should be bounded. Okay. It is just, yeah, it should be closed and bounded. Okay. There are more properties of compactness, which I will give as an assignment. We'll post it assignment, or we will discuss in the exam. Okay. There are many more properties. These are the standard properties which I have discussed in the class. Okay. There are more properties which will come as assignment and other things, and in the exam, problems as exam. Not properties, some consequences where you have to use the compactness. Okay. Basically, only these things we will use. Okay. Not anything, any new property. I mean, you have to use this to conclude those things. Okay. That's what, including finite intersection property. So now we will, so the examples of compact set we have already seen. It's all closed bounded sets in R and finite dimensional. I mean, any closed bounded set in finite dimensional normed linear space and all that. Okay. And we will come to infinite dimension. We will discuss one thing bit later. Before that, I have already said that the balls, the unit ball in L1, L2, L infinity, or even C0, they are all not compact. I have already shown this for all of them, because you just take the sequences with 1 at the nth place, zeros everywhere else, then that sequence does not have any subsequence which is convergent, because the distance between anything is a constant. It will be 2 root 2 1 1 here. Okay, because of that they are not compact. So on the other hand, this is also unit ball. So that means if unit ball is not compact, any ball is just a dilation of unit ball, or any other ball anywhere is just a translation and dilation, you will get it. So balls are not compact. Okay, open balls are not compact in this. This proof. Unit ball is not compact. We have already discussed this. I am just recalling. We have already proved this. You take the sequence En, this is nth place. Okay. Then this sequence does not have, En does not have a subsequence, convergent subsequence. Okay. So now you take C01. In C01, you say take this sequence, T power n. Okay. T power n is in C01. Okay. This T power n does not have a convergent subsequence. maybe I'll write it as a proposition, okay? Proposition. Unit ball, that is unit ball in C01 is not compact. What is unit ball? All those F in C01 such that norm of F infinity, well, equal to 1 we can show, or less than or equal to 1 is also fine. I mean, this is closed subset is not compact, means bigger closed set is also not compact. Okay. This is okay, is not compact. Okay. Unit ball, the same argument. Unit ball in C01 is
Not T0 is also sequential.
converging to 0. Okay. So why is C01? You take the sequence, proof of this is not compact. I mean, this is balls are being compact is what is called locally compact. We'll come to that. Okay. Locally compact means given any point, there is a neighborhood around it which is compact, which is equal to saying balls are compact. Okay, in metric spaces. Okay. I mean, we will dealing only with metric. Closed ball. Balls are not pre-compact. They are not totally bounded. Okay. Totally bounded, you don't need closeness or something, right? So balls are not totally bounded. That's what it says. Okay. So here C01, you take this Tn. This norm, this attains its maximum at 1, number 1, okay, in 0, 1. So this is contained in T power n, which is n equal to, these are functions, okay, T power n is a function, which is contained in C01, sorry, in that norm f equal to 1, okay, in this is okay, in this set, f such that norm of the unit ball contained in B01, okay. Okay. The open ball B01, maybe, sorry, it's a closed ball. Well, in normed space, it's fine. So in general, if you take a ball, XR, close it, this need not be same as all those X such that, I mean, y such that norm y minus X is less than or equal to, I mean, norm, not norm, dyx is less than or equal to R. In the discrete metric space, for example, it will not be true. Okay, general metric space, it is not true, but non-linear space, it will be true. Okay. That the closed ball is same as the closure. Okay. Okay. Any, I'm just saying that this is just all those F in C01. There's nothing such that norm F equal to 1. Okay. We want to show that this is not compact. I'm just saying this. Now I wrote a notation which need not be, it was just a remark. It's okay. Equal to 1, you can take, less than or equal to 1, you can take. If this is not compact, that is bigger, that cannot be compact. Okay, both are same. This is closed, that is also closed. If this is not compact, that is also not compact. Okay. When I define compactness, last class, when En is not there. But anyway, the proof is there, no? But there is nothing new in this. This same En, the same thing. It's okay, but even if it's not done, it is there, right? Yeah. It's the same proof. I mean, when I gave examples, these are non-examples. Okay? In examples in finite dimension is any closed and bounded set. These are non-examples where it's not the case, infinite dimension. In fact, in any normed linear space, infinite dimension normed linear space, the closed ball is not compact. Closed unit ball is not compact. You need little bit of functional analysis. Okay? So we will not do that. Okay? Minimal functional analysis. So now you take Tn. Okay, now Tn does not have this. Tn does not have convergent subsequence. Well, you can take the norm, or you can see that Tn converges to 0 for T in this 0, 1, and converges to 1 for T equal to 1, okay, as function. Point-wise, it converges to this function 0 and 1, which is not a continuous function, okay. So, suppose if it converges uniformly to some function, but since the point was, then it has to converge point-wise to such function, which is not happening. So, this does not converge uniformly. If it converges, if Tn converges to some function uniformly, then the limit has to be continuous, okay. So, and if it converges uniformly to some function, it has to converge pointwise also, but it converges pointwise to a discontinuous function, okay. I am not writing all the argument, but it's clear, right? Okay. Suppose Tn converges to something uniformly, then it has to be, the limit has to be continuous. And also it should converge pointwise also. Uniform convergence will imply pointwise convergence. Pointwise it is converging to something discontinuous. So it cannot converge uniformly. Okay, and in a subsequence also, same with subsequence. So this implies this does not have any convergent subsequence, so that's not compact.
How is that?
Huh?
Converging is not a continuous function, but it converges is not a continuous function. That means outside is
I mean, the argument is clear. Sit and try to argue yourself, it will be clear, okay. A very simple thing. Okay. So now we want to determine, so we want to give examples, get examples of subsets of C01, for example, okay, C0x, for example. We want to determine when it is compact. Okay, that's what Arzela-Ascoli theorem is. That's what we are going to discuss in the remaining time, hopefully. Okay. So for that, I need the definition. So from here onwards, I fix a compact metric space. Okay. I fix X is a compact metric space, and C of X all continuous function taking values either in real line or in complex numbers. Okay, I mean we will both are fine. Okay, then the definition, to take a collection of function, you take a collection of functions, a subclass of this is said to be equicontinuous if d of xy, there if given epsilon, there exists a delta greater than 0 such that d of xy less than delta imply the same condition, same thing, which is just the generalization of uniform continuity. Uniform continuity is given epsilon, there exists delta, delta does not depend on any x. Here it should not depend on any f also. This is a collection of function. You say a collection of function is equicontinuous. Okay, if d of f of x, f of y, or I mean or mod. Okay, here it is just we are using complex numbers or real numbers. Okay, less than epsilon. This is what is equicontinuous. If it is for a single function, that is what uniform continuous is. If it is, if you fix x and if you fix f, it is continuity. If you just fix f and vary x and y, it is what uniform continuity is. If you fix f and if it is holds for a collection of function, we say that collection of function is equicontinuous. They are all equicontinuous. Okay, it's for a collection of functions. Yeah, that's not true. That does not imply that.
This implies that.
This implies that. Correct. Yeah, of course. Uniform continuous implies continuous. Equicontinuous implies uniform continuous for all of them. Correct. Exactly. Exactly. Correct. Yeah. Correct. Hmm?
Yeah.
Of course. For all, that's the important thing. That exactly. Correct. And for all xy such that this, okay, such that for all xy in x such that again, okay, for all xy such that this is less than delta implies this is less than epsilon. For all f, okay, this is equivalent. The delta does not depend, I mean, it's continuous. There exists a delta given epsilon satisfying some condition. That delta does not depend on the point and also the function. So, as I said, if you have uniform continuity, if all of them are uniform continuity, need not imply that, but all of them as a single bond. For example, this is, if you have, this is Lipschitz continuous, right? If d maybe f of x minus f of y, okay, is less than or equal to k times d of xy. Okay. If some function satisfies this, okay, if f satisfies this, then it is uniformly continuous, single f. If it is true for all f, there is a single k, then it is equicontinuous. Okay. If all f, if for all f in f, this is true, then that is equicontinuous. This is one way. This is what is called Lipschitz continuous. This condition is what is called, I believe, spelling is okay, Lipschitz continuous. But there is a constant which is called Lipschitz constant. That constant has to be uniform. Suppose if there exists a, for each f there exists a kf, and that kf blows up, okay, then it will not be true. Okay, so you need a single constant. You can take the supremum of that k, that should work for everything. Okay, so I will come to this if I have time. Okay, maybe I will do this. Okay, I will just give an example. See, this is the kind of tell you that it's not, need not be always true. I mean, it's, so we know that, I mean, what I want to say is, if X be any metric space, okay, this is general, X be any metric space, and Fn C of X, okay, collection of continuous function, then there exists an equivalent metric such that each Fn is uniform continuous, or I mean Lipschitz continuous implies uniform continuous. Okay, Lipschitz continuous. So the proof is define I mean, let's take C xy, okay, x with d1, x with b, and y with rho, metric spaces. We have two metric spaces. I'm sorry to change. It is general, okay, metric spaces. We have two metric spaces, x with d, y with rho, and you have continuous function. C means continuous function from x to y. It's countable, Fn, n equal to, it's countable. I think you can do it uncountable, but provided this indexing set has to be nice. I mean, you should be able to integrate it or something. If it is compact, or you should be able to do the same, apply the same trick. We are going to sum something, you should be able to integrate it nicely, something like that. Okay, it should be possible. Okay, and let's not worry about it. For countable thing, define a new metric d prime of x and y. I mean, this metric depends on this Fn's, okay, equal to dxy plus summation n equal to 1 to infinity 1 by 2 power n. I mean, the thing is, first to see that it is true for one single function, you can take dxy plus d of f of x f of y. That will work for, you can make any function into Lipschitz continuous. Any continuous function in Lipschitz continuous, if you take the new metric as d of xy plus d of f of x comma f of y. Okay. Now we want to take the same thing, do the same thing for countable collection, but then that will not be, you have to sum it, but the sum will not converge. So for that we need to take this and we need to bound it, right? it is for these things only. Rho of Fn x, Fn y. 1 plus the same idea, Fn x, Fn y. Okay. Distance between Fn x and Fn y, rho, 1 plus this. This is bounded by 1. So 1 by 2 power n. So this converges. This sum converges. Huh?
Saying in equivalent metric to x.
Exactly. Yeah. This is equivalent to that. Okay. Convergence is same. That means open closed sets are same. That means open sets are same. Huh?
Same purpose.
Same topology. Yeah. I mean same topology. Equivalent means same topology.
But in the two are equivalent, the d1, d2 we defined in n.
They are equivalent. They both give discrete topology.
Yeah,
You know? Of course they are. I mean, there is a different definition. There is a constant between this and that. Usually for a norm, which depends on what definition we use. We say same topology is equivalent topology. Okay.
What do you mean by convergence?
That's what I said. For a single thing, you can just take a new metric, d of f of x, f of y. This will give you a new metric. Okay. But then you can't just add these things, go on adding these things because that will be infinite. So you have to take a new metric which looks like this, which is bounded. Then you have to put this 1 by 2 point. This is a standard thing. Okay. Mm. Mm.
That will be the Lipschitz.
Yeah, in the new metric, it's Lipschitz continuum. Correct. Yeah. You can make with a new metric, you can make it uniformly continuous. All those functions. Okay.
Here the Fn's are continuous or uniformly?
Continuous.
So any continuous function can be made uniformly continuous
With respect to an equivalent metric. That's all.
You also said another for equivalent, you said convergence should be safe.
Convergence, yeah.
But in d1 and d2, how is convergence?
Where in D1 and D2?
In
Convergence are same. Convergence means even same topology means convergence are same. What is it?
what do you
Sequence converging to X. Topologies are same. Implies closures are same. Convergence are same. Convergence is that you have a sequence, you add something that is close. It's same as that. Huh?
Yeah.
Yeah. Completeness is the Cauchy sequence. It's not about convergence.
But one of them converge, the other.
Where it doesn't converge. N doesn't converge in that metric, in that space. It converges to something. I said it converges to infinity intuitively, which is not in that space, right?
1 by
N. Then in that N, this sequence. In N, this sequence converges in D2, not convergence. It's Cauchy in D2. It's not Cauchy in D1. There is no 1 by n in N. It is N. Yeah. That's what the remark is. That is in the assignment also. I am not sure whether I gave the same thing. It's here, no?
Okay.
Where I wrote somewhere. Where did I write? Okay, I will just write it here. Okay. Then d of Fn, sorry, this is d prime, right? D prime of x and y is less than or equal to it's other way. Sorry. Yeah. Rho of Fn x, Fn y is less than or equal to 2 power n d of xy. Okay. This is Lipschitz continuous. Rho of f of x, f of y is less than k times d of xy. If you have a k here, instead of Fn, you have this from this definition, it follows this, right? Rho of this is less than or equal to this, which is less than or equal to 2 power n this. Right? Huh? You just write it, pa. It is same inequality, 8th standard inequality. Unless you find a fault with this. Huh? It's just the inequality. Huh? Not with the same K. If we do that, then that is not true. Tn, that will not be true, right? That is a countable collection. If you make all of them Lipschitz continuous with something, that will mean they are all equicontinuous. If you make with respect with the same K, here too, this is just to show you, you can make it like this. This is just to show you that you can make this collection Lipschitz continuous, but not uniformly Lipschitz continuous, which is what is called equicontinuous, which means equicontinuous, because this 2 power n will blow up.
D or D prime?
This is D prime. Sorry. Any countable collection of no, not equicontinuous, Lipschitz continuous. Each one of them will be Lipschitz continuous. A finite one you can do. Any finite one, if it is uniformly continuous, there is anyway Lipschitz continuous. Each one of them is uniform continuous. On a compact set, for example, if X is compact, they are automatically uniform continuous. Yeah. So if you have a compact set, compact metric space, any single function is uniformly continuous, equivalent to equicontinuous. Of course, single function there is nothing. And if you have a finite collection, that is also equicontinuous. If they are all uniformly continuous, so automatically finite collection equicontinuous is automatic. Okay, only for infinite collection. You don't need even Lipschitz continuous, just uniform continuous. Each one of them is uniform continuous is fine. Okay, you just have to take the minimum of the delta. That's all. Okay. This is done. Okay, this is just to show you that we can actually do something for the collection, each one, but we cannot take the uniform. If we take, as you asked, if we take uniform 2 power n, that will mean that we can make any countable collection as equicontinuous with respect to equivalent metric. And so, no, I mean, this is just an exercise. Okay, maybe I should give an assignment. This is equivalent metric. You should see that the two metrics are equivalent. Okay. Huh? This was given as exercise? No. Yeah, each one of them. Yeah, correct. You are right. I gave for one of them. Now you have the sum. You just have something bigger. No, that is true. That is true. I gave an exercise. For one of them, it is just the sum of them. That's the difference.
The sum also you need.
Did I? Okay. 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 So another example of equicontinuous. XY both compact. XY both compact. And if you have a F from X cross Y is also compact, right? You can take the product metric, whatever. You can sum the metric, or you take the square, sum the squares and take the square root, or you take the maximum. There are 3 ways we can do, which I call D1, D2, D infinity, whatever. They are all same thing. They give the same topology. So X cross Y is also compact. If you have a double sequence, then I mean that converges if and only if coordinates with converges. The first one will converge. First one will have a convergence subsequence because it's compact. You take that subsequence and that will have a further subsequence here, which will be convergent. So you will have a convergence subsequence of the bigger one. I mean, it's just to prove that X cross Y is compact. You can actually prove infinite product is also compact, which is called Tikhonov's theorem. But any purpose. If you take any product, if you take Xi, okay, with I, if you take the product, this is product, not X, okay. Maybe this is Ki. Ki's are compact. I in I. Any arbitrary product, then you have to define what is a product topology on that, not metric, topology. Okay, that product that is compact, which is what is called Tikhonov's theorem. You will see in the topology course next year, or I can prove it if you don't need. Okay, you see later. Okay, hopefully you will get proved. Okay. Okay, XY both compact, then this is also compact, that is clear. As I said, any sequence here will have a subsequence. You can use that argument. Okay, to what do you want? C, let's say C, okay, is continuous. Okay. Then you define f y at x equal to f at x y. Okay. For y, fix y in 1. Okay. You have this. You have a collection of function. Then this function fy, this is a collection of function, right? Y in y is equicontinuous. Okay. You take any metric, d1. I said d1. I said it sometime back. We have three choices. You can have d1, d2, d infinity, which I defined on this. You can take any one of them. Okay.
Continuity.
Huh?
So the continuity depends on the
The which one?
that is continuous.
Continuity you can define for topological space, but I am saying you can take any metric on this d1, d2, d infinity. Okay, product topology. Huh? Yeah, but equicontinuous I am defining only on x. Equicontinuous I am only defining on x. Okay, I mean this is just f is continuous. Okay, both any three metric I said. Okay, the product metric. It is just the product topology, whatever induced by three metrics which I said which induces the same product topology. So if f is continuous equivalent to yeah, uncountable, doesn't matter. What is the definition? Where is the definition? Oh, there is no countable. Okay, so given epsilon greater than 0, which is equivalent to saying given f is continuous, which is means x cross y is compact, so it is uniformly continuous. Okay, given epsilon greater than 0, there exists delta greater than 0, such that x minus x prime, sorry, I have to use d, sorry, d of x dx of xy less than dxx prime less than delta dy y prime less than delta implies that is to okay, f of xy minus f of x prime y prime epsilon. Okay, that's what continuity means. Okay, now you take y equal to y prime. Of course, then dy prime is 0, which is less than delta, so it's okay. So y equal to y prime. This implies there exists given epsilon. This is just direct definition. Given epsilon greater than 0, there exists delta greater than 0, such dxx prime is less than delta implies fyx minus just same as this fyx prime is less than epsilon. So this is what is for all y. Just write the definition of continuity, you get this. Okay. So if you have a continuous function in the product topology, then you get a single variable, two variable function. If you have a two variable function continuous, then you get a function collection of functions in one variable that is equicontinuous. Okay. Then another, so as I said, if you have a collection which is uniformly Lipschitz continuous, that the constant k is uniform, then that collection is equicontinuous, I said. Okay, so that we can get an example for that. Okay. Example is another example. You take this collection f, this is C01. With respect to product metric, you take one of the product metric, okay? F in C101 such that f prime t is less than m. Less than or equal to m, doesn't matter. All bounded, you have a bounded collection, okay, which are differentiable, and the derivative is all continuous. Okay, so now you have f of t minus f of s is less than or equal to f prime of some s naught times mod t minus s. S naught is in proposition is this is a is equicontinuous. Example of equicontinuous. Okay. Now this implies so where the s naught is in Ts. Okay, but this is less than m. This is less than m. So this implies f of t minus f of s is less than or equal to some m times mod t minus s. There is a for all f in that collection, you call it script f. Okay. If you call that a script f, then for all functions in the script f, this is satisfied. Okay. You are fixing a. I take all functions such that which are bounded, the derivative is bounded. Then f prime s naught is in the interval t and s, such that mean value theorem. Mean value theorem.
Bounded is the same bound for all.
Exactly, that's what same bound.
Given at this
Yeah. F
bound for the derivative.
bound for the derivative. Yeah. Uniform constant for it. It's not universal. Uniform constant. Uniform for this collection. Yeah. Okay, let me finish it fast. I will take some more time. I missed few classes, nearly half a month. So I use this theorem. Arzela Ascoli theorem. Okay. Any problem? Okay. So I take a script f contained in C of x. X is compact. Okay. You have a compact metric space X. I take a collection in C of x. Okay, is compact. So X is compact, then C of x is, I didn't mention it. C of x is contained in B of x, right? All bounded functions on x. Any continuous function on a compact set is bounded, okay, because it's closed, range is closed and bounded, so it's bounded. So C of x is contained in B of x. So and it is closed also. All continuous, I mean uniform limit of continuous function is continuous. So because of that, this is complete. C of x is a complete metric space. Okay, C of x is complete. I mean, I should have mentioned. I said that C01 is complete when I gave example. C of x for any compact set is also complete. That's because it is contained in B of x and it is closed and it's closed inside that. Because any function on a compact set is bounded. C of x is not compact. Where I said C of x is? F contained in this is compact. Okay? F contained in C of x is compact. Property of what? No, I haven't finished the thing. This is, I am going to give an equivalent condition. I am just remarking that this is a complete metric space. F is any subset is compact. If and only if F is closed, of course, any compact set is closed, bounded. Here, bounded means bounded in C of x. Okay, that means it is uniformly bounded. Let me come to that. Okay, and equicontinuous. This is if you have a collection of continuous functions on a compact metric space, that collection is compact. Okay, now see x is a metric space, compact metric space. C of x is non-linear space, which is a compact metric space. Sorry, which is a metric space. Any subset, any sub collection. Okay, if it is, of course, if it is inside a finite dimensional thing, that is anyway closed and bounded is enough. But it could be something like a subset of unit. It may have come from some infinite dimension. Okay, then it is compact if and only if it is uniformly equicontinuous, closed, bounded, and equicontinuous. There are three conditions. Closed bounded is clear, equicontinuous is one more condition. That's all. Yeah. So that is here bounded means bounded means uniformly bounded. That is norm F infinity is less than M for F. Not each one of them is bounded. As it's bounded as a subset of C of X. C of X is a non-linear space. In that non-linear space, it is bounded. That means norm F infinity is less than M for all F in M. It's uniformly bounded.
Suppose if it was finite dimensional, then we wouldn't really need the equivalent.
Of course, finite. I mean, if it comes from a finite dimension.
Yeah.
In general, in a finite dimensional vector space, there is no equivalent. There is no notion of equivalent. Only for function space, this makes sense.
Actually uniformly bounded. Or are these two equivalent?
No, bounded means uniform bounded. Bounded in C of X, I said. Bounded in C of X is just a remark. I have said closed and bounded. Bounded as a metric space, not function. Already functions are there, but you may get confused with that function boundedness. But I am saying it is bounded in a metric space. Bounded in a metric space means that is a definition, right? That set has a diameter, finite diameter. That's what it means. That is equivalent to saying this is norm F infinity is less than M. If you have any compact metric space, then the subset is also, I mean, if you have any metric space, a subset is compact, it will imply it is closed and bounded. It closed and bounded in the metric space. That means it has a finite diameter. So that is exactly equal to finite diameter in the metric space. That is same as it is uniformly bounded as functions. Okay, not bounded function. Huh? Yeah, one of the directions. Let's see. Okay, let's prove this, which is easier. Okay, so is compact. F is compact. Of course, closed and boundedness is clear. For any compactness, it is true. We only have to prove equicontinuous. Okay, so E is compact. So we only need to prove F is equicontinuous. Okay, to prove equicontinuous, so this is totally bounded. Okay. That is, there exists F1 up to Fn in script F, such that script F is contained in B of F given epsilon greater than 0. Given epsilon greater than 0, there exists such that the open balls Fi epsilon, open ball B of Fi epsilon, the union of that contains that F. That's what totally bounded is. It's compact, so there exists totally bounded. Okay, and each Fi is uniformly continuous because it's compact. Continuous. Okay, by definition, I mean, Fi is on compact set, it is continuous, means it's uniformly continuous. Okay. Given epsilon greater than 0, that is totally boundedness. That is totally boundedness means F is totally bounded. So given epsilon, there exists F1 up to Fn such that this happens. This union of the open balls contains that F. Okay. Now each Fi is uniformly continuous. Okay. So I epsilon is fixed. So there exists a delta I such that d of xy less than delta imply d of Fix, Fiy. Now you just have to take less than epsilon. Okay, or d, I mean, d means it is just it is complex number. So f of Fix minus f of Fiy is less than epsilon. Okay. Now you take, let delta equal to minimum of the delta I. Okay. Now this delta should work for the equicontinuity. That's clear, right? Now if dxy less than delta, okay, and f is in f, let f is in f, then f is in one of those things, fi epsilon, okay, that is d of, mod of f, mod of norm of f minus fi infinity is less than epsilon, okay, for some I. Okay. F is in script f means it should be in one of them because the union covers that. So then this is true. Now it is just f of x minus f of y is less than or equal to f of x minus fix minus fiy plus fiy minus f of x. Okay. This is less than epsilon, this is less than epsilon, this is less than epsilon. If d of xy is less than delta, then this whole thing is less than 3 epsilon. Okay. If you want, you take that to be, that's okay. You need to get some number times epsilon. Okay. If you want, you take that as epsilon by 3, it will work. Okay. Okay, this is fine. This should be an exercise. Okay. Epsilon by 3 trick. Okay. So one way is easy. Okay. We prove the non-trivial direction. Okay. Now we want to prove this. Okay. Now we assume f is closed, bounded, and equicontinuous. When we want to prove that this is compact, all closed is already there. We only need to prove closed means it's complete. Okay, because C of x is complete, closed means it's complete. We only have to prove, only need to prove this is f is totally bounded. This proof should mention, this proof is by Kumaresan, I think. I think it's due to him. I think so. Because in any book, anywhere, I think the original proof is to prove that this is f is sequentially compact. That's what is proved everywhere, as far as I see. But in his book, it's totally bounded, which is much easier. Much easier means it's not messy. It's very direct. Proving totally bounded, as you can see. Okay. I think the idea is due to him, and it is in the book also. You can see. Okay. That's what I have been using all these years. Okay. The last 20 years, I'm using this proof only. Okay. Okay. So we need to prove it's totally bounded. Okay. That is, we have to have finite, given epsilon, we have given epsilon or 5 epsilon, 6 epsilon, 7 epsilon, doesn't matter. Okay. We need to have finitely many balls which would cover that, cover this F. That's what we need. Okay. Okay. So for that, we define that is script F. So let us use this B. No, before that, I need the following. X is compact, X is totally bounded. So its equicontinuous is given. So there is a given, see, we need to prove this is totally bounded. That means given epsilon, maybe some number times epsilon, 5 epsilon or something, given 5, because otherwise I have to take epsilon by 5 or something. So let's take some epsilon, some number times epsilon, constant times epsilon. We have to cover this by finitely many open balls of radius that number times epsilon. Okay, that times epsilon. Okay, so let us fix that epsilon greater than 0. So there exists a delta greater than 0 such that this d of f of x mod of f of x minus f of y is less than epsilon if d of xy is less than delta. So given epsilon, we have got a delta. Now for this delta, since x is compact, there exists x1 up to xn in x such that x is equal to union of p of xi delta. Okay, because x is totally bounded. Okay. Now, so this is bounded. The set is bounded. Let norm f infinity is less than or equal to m for all f in script f. I mean, we know that that is uniformly bounded, so m be that bound. Okay. Now this, I mean, I'm taking this because it may be complex numbers, which is contained in C or R. R means it is just minus mm. Okay, otherwise because it's complex number, it may be this. Okay, so now this is compact. Take the closure is compact. Okay, so there exists y1, y2 up to ym in B0 m, the closed ball 0 m. Okay, such that B0 m closure is contained in union of maybe ym, yeah, I equal j equal to 1 to m, B0, B y epsilon. Okay. Because that is compact, that is totally bounded. So we have x which is compact. Okay. The function is defined from x to complex numbers, and they are all uniformly bounded. So they land up within an open ball of radius m. Okay. So all these f's here in this script f, okay, are functions from x to the closed ball B0 m. Okay, so both are compact. The range is compact. This is compact. Okay, so both I just cover it with finite number of open balls. So I have x1 up to xn, y1 up to ym. Okay, now you take this collection, all those maybe alpha from xi equal to 1 to n to yj, j equal to 1 to m. This is finitely many functions. It's a finite collection. Huh? Functions. Okay. Then this is the cardinality. Okay. By this I mean cardinality or number of elements or whatever. Okay. This is equal to n power m, right? The first one has m choice, second one has m choice. There are n such thing, n power m. Finite. Okay. It doesn't matter. It's finite. Okay. When I didn't change, I have changed. Yeah. Huh? M to the n. First one will have m. Yeah, m. First one will have m thing. Second one will have m, so it will m to the n. Correct. Doesn't matter. It's finite what we need. Okay, it's finite. Okay, what do we want to? So this is true. Then okay, I'll go there. A is all collection of functions from xi. We have got x1 up to xn, y1 up to yj, ym. Okay, it is just a collection of functions between them. Okay,
What is alpha?
alpha is a function. You instead of writing like this, I have written like this. I mean, what's okay? Alpha is a collection of function from x1 up to xn to y1 up to ym. Okay, just a collection of functions. I was said it 2, 3 times. Good. I said it. First line itself. Okay. Now you define Q alpha, all those F in C0. I think we can take it. Otherwise, we will take it in F. I think this will work. C0 F such that R of F of this is alpha is fixed. Okay. Alpha is a function here. Okay. Such that F of xi minus alpha of xi is less than epsilon for all I. For all I. Okay. What is what? I have just written it. No, all those f such that this happens. Given a function alpha, you have this. Yi is all those y1 up to yn, which covers the ball 0m in complex numbers. It is just a function from x to ball and 0. All functions, they are all bounded function, uniformly bounded function. So they all land up within the ball of radius m in the complex plane. Okay, it is just a function from x1 up to x to the ball. This is compact, that is compact. So this can be covered by finite number of balls of radius delta. That can be covered by finite number of balls with radius epsilon, where epsilon and delta are given by the equicontinuity. Epsilon is fixed. Okay, epsilon is fixed. We want to prove this is totally bounded. Our aim is to prove this f is totally, this script f that is compact we want to prove. It's already closed, so it's complete. We have to prove it's totally bounded. So for that we need to cover that. Okay, this is what will cover that. Okay. Okay. Maybe you can take it less than epsilon if you wish, but then you can take a bigger open ball than this and work with that. Okay. Okay. Now U alpha is this. Huh? If it is empty, it doesn't matter. Okay. I mean, if it covers, some of them has to be empty. Okay. Those are balls in X, of course. Those are balls in R or C. Yeah. C. I mean, I have used because otherwise I can use the interval minus, I said this, minus mm. Yeah. Okay. And delta is given by the equicontinuity, which is very important. Given epsilon, the delta is given by equicontinuity. Okay. Now U alpha. U alpha is this. Now the claim is the script f is contained in union of alpha in A, U alpha. Okay. This is union, that is U alpha. This is the claim. Okay. But that is easy, I think. So if f is in F, okay, then you have to prove that that is in one of those U alpha. Okay. Then, I mean, if then f of xi, okay, be in one of those for xi, for I, f of xi is going to be in one of those. Okay. Then let me write it as that. For f in F, define alpha in A such that alpha of xi equal to yj if f of xi lands in P of yj. F of xj is going to land up in some yj epsilon. Then you define alpha of xi equal to yj. For each xi, this is true. Okay. Huh?
What if it is there in many? Like,
How can it be in many? Huh?
like P of yj,
Yeah.
they will cover.
Correct, correct.
They might intersect. So like if it's in many,
Choose one of them. One of them. Okay.
That well defined.
No, you make it well defined. You choose one of them. minimum, you choose one of them, it's fine. Use something which satisfies that condition is what we need. Okay, you choose one for function. Okay, that's okay. I mean, you define such that this happens. That's all. Okay, then okay, then we want to prove that f is in u alpha. Then f of xi minus alpha xi, okay, is equal to, sorry, no, that it is just done, no, alpha xi, f of xi minus alpha xi, alpha xi is yj, f of xi is less than epsilon, right? Right, that's all, no? It's direct, there is nothing to prove. So this implies f is in, I mean, this implies this proves this, hence the claim. Given any f, it's in one of those u alpha. Okay, hence the claim. That's all. There is nothing in this. It is just direct. Hence the claim. If you have any f here, it is in one of those u alpha where alpha can be chosen by this. Okay, f of xj has to be in one of them. It's chosen by that. Now, if you prove that this has some constant times epsilon diameter, then you can take a slightly one more epsilon you can add, and that big ball you can take. Let's just like that. Okay, so claim is diameter of u alpha is less than or equal to 4. Okay, so something in u alpha means f of xi, u alpha definition, that is u of definition is here, f of xi minus alpha xi is less than epsilon. Okay, so something is u alpha. So if you have f and g u alpha, remember it has to, we have to show that the norm, difference of the norm between them. Okay, then f of x minus g of x is less than or equal to 4 triangle inequality, f of x minus f of xi, which is f of x minus f of xi. So yeah, I mean, x is there, then x is going to be in one of those, right? F of xi delta. Okay. This is the claim. Claim, this is the. Then to prove this, you have to take f and g in this. Then yeah, we are proving it. If this is less than something, 4 epsilon for all. I take f and g in this. Then you take a x has to be in one of those xi delta. Okay. Now f of x minus g of x is less than or equal to f of x minus f of xi. Then plus f of xi minus g of xi. Okay. F of xi minus alpha of xi. Okay. Plus alpha of xi minus g of xi plus g of xi minus g of x. Okay. Now, by eq continuity, x is in b of xi delta. By eq continuity of f and g, these two are less than epsilon. Okay. Now, this is in u alpha, so these two are less than epsilon. The whole thing is less than 4 epsilon. We have already have all the ingredient there. This is less than epsilon by eq continuity. These two, the same delta works further. These two are eq by eq only. This is less than epsilon. This is less than epsilon. Because they are in u alpha, by the definition, these two are less than epsilon. So the whole thing is 4 epsilon. Okay. Now all we need to prove is the following. Huh? You have that? Yeah. We have just shown. We have just shown this. Claim. So claim f is contained in B of, you take something from u alpha. B of alpha. You always ask once the proof is over and we go somewhere. It's just proved that, no? That is a claim. It is clearly written. Alpha. Okay. Yeah. If you want. That's all. This is totally bound. If you now you ask any doubt, I need to give one example. Shall I take time or stop? Because it's a continuation of this. Huh?
So can we do the example next class because then we'll also revise.
Okay. So you can go through the proof. In the book is also, it's in the Kumarason's book also. I've just reproduced the same. I haven't seen this proof anywhere else. You can look at the sequentially compact proof from some other book. Compare. I think this is better. You can take a picture. You can take a picture of me also. Yeah.